Manipulation gave us a local path-based attribution. Functional ANOVA takes the complementary global view. It characterizes how much each hyperparameter contributes to performance variance across the entire configuration space by an orthogonal functional decomposition. The global question: if we draw configurations uniformly from the search space, how much does varying a given hyperparameter change expected performance? Equivalently, how much of the variance in the cost is attributable to that hyperparameter? This targets three things ablation could not. First, which hyperparameters drive variance across the whole space rather than along one path? Second, which are globally irrelevant regardless of the context? And third, whether there are interactions that actually matter. Functional ANOVA answers all three within a single variance decomposition framework. The formal object is the ANOVA decomposition. Under mutual independence of the hyperparameters, the cost function admits a unique decomposition into orthogonal components. First a grand mean f0, then a sum of univariate main effects functions fi, a sum of bivariate interaction functions fij, and so on and so forth with the higher order terms. Each component is defined by marginalization. f0 is the expectation of the cost over the whole space. The main effect fi of hyperparameter I is the conditional expectation of the cost given lambda I, marginalizing over everything else minus f0. The pairwise term fij is the joint conditional expectation minus the two main effects and the grand mean, that is, the residual interaction after removing lower order structure. Because the components are mutually orthogonal, the variance of the cost decomposes additively. The total variance equals the sum of the main effect variances vi plus the pairwise variances vij plus higher order terms. This is the functional analog of classical ANOVA, only that the factors are continuous functions of the hyperparameter values. Given the variance decomposition, importance is defined by normalization. The main effect importance ii is vi over the total variance. The fraction of variance explained by hyperparameter I in isolation. The interaction importance iij is vij over the total variance, and so on and so forth. The properties follow from orthogonality. Each I lies in the unit interval, and the full set of terms sums to at most 1, with equality when the decomposition is complete. A large main effect importance identifies a dominant driver of variability. A small one identifies a hyperparameter to which performance is essentially insensitive marginally. A large interaction importance flags a pair whose joint effect exceeds their individual contributions. Let's have a look at a concrete example. Tuning gradient boosting of a learning rate, max depth, number of estimators, and subsample on a deliberately noisy benchmark with a random forest surrogate fit on 150 evaluated configurations. The decomposition attributes roughly 95% of the performance variance to max depth and learning rate jointly. The number of estimators is near irrelevant. The gap between each main effect bar and the total effect bar is the interaction share, which here is very small. The surface is close to additive. The actionable reading under a constrained tuning budget prioritized depth and learning rate and effectively fixed the number of estimators. The computational obstacle? The cost is expensive to evaluate, yet the decomposition requires integrating over the configuration space. Hatta et al. Resolved this by fitting a random forest surrogate on the HPO observation history and computing importances from the surrogate. The choice of a random forest is not incidental. It is what makes the marginalization tractable in closed form. Within any tree, the prediction is piecewise constant over axis-aligned regions. So the marginal of a continuous hyperparameter is an exact weighted sum over leaf predictions rather than a numerical integral, and a categorical hyperparameter is handled by a finite average over its levels. Consequently, the marginal functions and hence the variance terms are obtained analytically rather than by Monte Carlo sampling. The marginalized surrogate for hyperparameter I is the expectation of the surrogate over the complementary hyperparameters holding lambda I fixed. Empirically, it's estimated by averaging the surrogate over sampled or enumerated settings of the remaining hyperparameters. Though, as noted, the tree structure lets us do this exactly. The main effect variance is then simply the variance of the marginal function taken over the domain of lambda I. A flat marginal implies negligible importance, a marginal with large excursions implies high importance. Interactions are computed by the same marginalization with an orthogonalization step. For a pair, take the joint conditional expectation of the surrogate given both hyperparameters, then subtract the two main effects and the grand mean. What remains is the pure interaction component, the structure not explained by either hyperparameter alone, and its variance Vij quantifies the interaction's contribution. A practically important refinement is fANOVA. Standard fANOVA marginalizes over the entire configuration space, including regions of arbitrarily poor performance that no practitioner would ever target. As a result, the importances can be dominated by variance in irrelevant bad regions. fANOVA from Watanabe et al. Restricts the marginalization to the promising subspace near the incumbent. Formally, it weights the integration by a performance threshold indicator, conditioning on the surrogate prediction falling below a certain threshold tau, for instance, the top 10% of the observed costs. The resulting importances answer a sharper question. Which hyperparameters matter conditional on searching for a good configuration, rather than averaged over the whole space, including regions one would never visit? But of course, fANOVA also comes with its limitations. 4 assumptions that might be worth flagging. First, the decomposition presumes mutual independence of the hyperparameters, which is violated in conditional or hierarchical search spaces as we have them, for example, in the combined algorithm selection and hyperparameter optimization problem. Second, importances are computed from the surrogate, not the true cost, so surrogate misfit propagates directly into bias in the scores. Third, the number of interaction terms grows combinatorially. So beyond pairwise, the computation is typically intractable for large D, and higher order structure is typically omitted. Fourth, and most consequential, these are global averages. A hyperparameter may be critical in one subregion and irrelevant elsewhere, and a single global I averages over that heterogeneity, potentially misleading a practitioner who targets a specific subregion. To summarize, functional ANOVA delivers global variance-based importance by decomposing the variance of the cost into main effects and interactions, identifying which hyperparameters drive variability across the space. The random forest surrogate is what renders it practical, yielding closed-form importances from the HPO history with no additional cost evaluations. fANOVA improves practitioner relevance by restricting attention to the promising subspace. The standing limitations are the independence assumption, dependence on surrogate quality, and the fact that global averages can obscure local structure.